We can represent sound waves from a tuning fork moving essentially in one dimension, and that's what this diagram is here. We'll play with some tuning forks in class. But what I have on the left side is a tuning fork, and you can imagine I've captured the waves of the tuning fork in a tube, and I've got compressions and rarefactions shown and a wavelength that's illustrated. So far we've been talking about the spatial parts of the waves. Spatial, S-P-A-C-I-A-L, the parts of the wave that I can measure with a ruler. But there are also parts of a wave that I can measure with a stopwatch. So I want to illustrate that here. So we'll go back to this diagram in which we've got our wave that is oscillating. We'll talk about the time parts of waves. Now up here at the top, I've got a way I can adjust the frequency. And we'll see that if I increase the frequency, then what happens is that the shaking happens faster and faster. Whereas if I decrease the frequency, the shaking happens lower and lower. When we talk about frequency, we talk about the number of vibrations per second. There is another time characteristic of waves that is the reciprocal of the frequency. It is called the period of the wave, and we represent the period with the letter capital T. And the frequency and the period are inverses of each other. The language that we use for waves is a little bit awkward, but we will still refer to that language throughout this course. It turns out that there's a relationship between the spatial part of the wave and the temporal part of the wave, and that relationship is called the wave equation. We say that the speed of the wave is the distance one wavelength would travel in one period. And so we can write the wave equation as V, standing for the speed of the wave, is equal to lambda divided by T. This is going to be one of the important equations that you use when you deal with waves. But there's a reciprocal relationship between frequency and period. That's going to be another important relationship. Frequency is the reciprocal of the period. Again, when we say frequency, we're talking about the number of vibrations per second, whereas the period is the number of seconds per vibration, how much time it takes for one vibration. If I feed this frequency into the wave equation, then I come up with the more common form that you're going to see that relates wave speed, wavelength, and frequency. And it looks like this. Speed is equal to wavelength times frequency. And you see now we have linked together the spatial part of the wave, the wavelength, with the temporal part of the wave, either the frequency or the period. We now want to discuss the behavior of waves when it begins to encounter different materials. And this is a topic that is called reflection. You're familiar with reflection because you look at your reflection every morning in the mirror when you get ready to come to school. We define the reflection of a wave to be the return of a wave into the original material when it encounters a boundary. When you think about looking in a mirror, as you're gazing at the mirror, the light that is incident into your eye actually has bounced off a piece of glass. So there's an interface between air and glass. So what happens is some light that has scattered off of your face, maybe that light originated from the light bulb that's in your bathroom, it bounces off your face. Those electromagnetic waves that we call light waves now leave your face and they travel in all directions, and some of those waves strike from the air onto this piece of glass and they bounce, and some of those bouncing waves come back toward you and enter your eye, and when they enter your eye they form an image because they stimulate the retina of your eye in a way that causes you to be able to interpret that as the reflection of your face in the mirror. So now what's happening is that wave that is entering your eye is called the reflected wave. We want to look at what happens when a wave gets to the interface between two different materials. And there are going to be two types of reflection that we're going to see. So we're going to return to this simulation. We have over here on this side our string attached to a sliding bar. So there's a ring that's along here, and we're going to call that a loose end. I'm going to send a pulse down. That's going to be a crest that goes down. This bar over here is going to represent our new medium. In other words, there's a different material besides a spring or a string that the wave encounters. It's going to behave in a certain way. So here we go. We're going to send down a pulse. I'm going to send a crest down. It reflects, and a crest comes back. We say when there is a loose end, there is no phase shift of the wave when the reflection occurs. This is called reflection off a soft boundary. When I send a pulse down or a wave down and it encounters a soft boundary, then the reflected wave experiences no phase shift. If I send a crest down, I'm going to get a crest back. If I send a trough down, I'm going to get a trough back. This is likewise true for longitudinal waves. If I send a compression down and it hits a soft boundary, I'm going to get a compression that reflects. Or if I send a rarefaction down and it hits a soft boundary, then a rarefaction is going to come back. The opposite thing happens when I put in a fixed end. So now I'm going to change my boundary and I'm going to clamp rigidly the end down here. I send a crest down, a trough comes back. And so we say that there is a pi phase shift or 180-degree phase shift, or sometimes you'll even hear it just referred to as a phase shift. When a wave reflects off of a hard boundary, then you get a pi phase shift, or you get a phase shift occurring. When I send a wave towards a hard boundary, then the reflected wave experiences a pi phase shift. If I send a crest down for a transverse wave, a trough will come back. If I send a compression down in a longitudinal wave, a rarefaction is going to come back. This behavior on reflection is true whether I have a one-dimensional wave, a two-dimensional wave, or a three-dimensional wave. So far we've been talking about one dimension. What I like to do now is to talk about two dimensions. So I want to sketch a series of plane waves that are encountering a boundary. You might imagine that this boundary is a piece of glass that's been set up in air. So we could talk about light waves. And the boundary is the top part of the glass. Let's imagine that I have some waves that are incident from the left side at an angle that's going to hit this boundary. So I'm going to draw a ray that represents the direction of travel of these waves. That ray represents the direction that these wave fronts are going to travel. So I'm going to show some plane waves that are traveling in that direction. It's shown on page 177. It's the diagram that's in the middle of the page. Alright, so you can imagine that I'm showing the crests of a light wave. Light happens to be a transverse wave. You might imagine that I'm showing the compressions of a sound wave. Sound is a longitudinal wave. That's some good facts to know. Light is transverse, sound is longitudinal. I would call these that are approaching the boundary the incident waves. They're traveling at some angle with respect to this boundary. And they hit the boundary. And when they do, they're going to bounce. They're going to reflect. And there's something that's called the law of reflection. And we want to develop that. First, we need to sketch some more lines. The first thing we do is we find where the incident ray, that's that ray that's perpendicular to the wave fronts, the one that has the arrow on it, the place where it strikes the boundary, we're going to sketch a line that is normal to the boundary, perpendicular to the boundary. Once I've sketched that normal line, there are a couple of angles that I could measure. And the one that we want to measure is the angle that is between the normal line and the incident wave. We will call that angle the angle of incidence. And we label it with a theta that has a subscript I. Theta meaning angle and I meaning incidence. Now, I could measure that angle using a protractor. In fact, I already have measured that angle. That angle turns out to be 50 degrees. Now there's something that's called the law of reflection. And what the law of reflection says is that the angle of reflection, in other words, the angle at which this wave is going to reflect off this boundary, is going to be equal to that angle of incidence. So that law of reflection says that theta r, which is going to represent the angle of reflection, is equal to theta I. That's an important relationship. It's known as the law of reflection. If I wanted to sketch what the reflected ray looks like, I would have to measure from the normal on the right-hand side an angle of 50 degrees, because again, I've said this is a 50-degree angle. Then I would sketch the reflected ray, and that's what I'm going to do. So on this right-hand side, I have the reflected ray. I have the angle of reflection, which again is measured with respect to the normal, and that happens to be equal to 50 degrees in this case. And now I'm showing the crests from this reflection in that diagram. The law of reflection, and that happens whether it's in 1 dimension or 2 dimensions or 3 dimensions. I've shown it in 2 dimensions here. Now you notice I've said incident waves on the left-hand side. The waves are the wave fronts. On the right-hand side I've said reflected ray. Those are actually reflected waves as well. The reflected ray is that line that has the arrow on it, and the waves are the wave fronts. So I could talk about the incident ray or the incident waves, and I could talk about the reflected ray or the reflected waves. The idea is the law of reflection applies in either case. It turns out the law of reflection applies whether I have a smooth surface, like I've sketched here, or a rough surface. And we can talk about smooth surface reflection, which is going to be known as specular reflection. And we can talk about rough surface reflection, which is called diffuse reflection. That will be a topic that will come up in a later lesson. Now we want to discuss a topic of what happens when waves begin to interact with each other. That is called interference. We say that interference occurs when 2 or more waves, usually 2 is all you're going to be worried about in this course, try to occupy the same space at the same time. Waves are carrying energy, and that energy disturbs the medium. The medium itself is disturbed as that energy passes through it, and then it returns to its original state, unless there are continual disturbances that come along. But what happens when 2 disturbances try to occupy the same space at the same time? It turns out that we've got interference going on. So we're going to try to illustrate that, simulate that with our simulator again. I'm going to let this system oscillate. I'm sending down pulses. They are reflecting, and now I have pulses that are traveling to the right at the same time that reflected pulses are traveling to the left. So I've got incident waves going down, and I have incident waves coming back. And if I fix things just right, then I can get a pattern that appears to have oscillations that are not really moving along. I've got a pattern that is regular. There are places where there's not much oscillation going on, and there are other places where there's maximum oscillation going on. These places where there's maximum oscillation we're going to refer to as antinodes, and the places where there's very little oscillation going on we're going to call nodes. What I would like to do is to have you imagine that I take a time-lapse photograph of this situation. And in fact, this is a demonstration that we'll do in class with a string. We'll put standing waves on a string. And as I sweep out this pattern, then there's going to be a certain result that occurs. And we'll show that here. Here is the sort of pattern that is traced out if you have a time-lapse photograph of that oscillation pattern that we saw just a moment ago. How is that occurring? In order to do that, we have to talk about the interference of these 2 waves. Let's discuss what happens in a time-lapse sort of wave. Let's suppose that I have a one-dimensional system, like a string or a spring, and I send waves down simultaneously from both ends. Here's the equilibrium position. From the left end, I'm going to send down a crest. We're going to call this crest A. At the same time somebody shakes the left end of the spring into a crest, somebody else standing at the other end of the spring is also going to shake down a crest. We're going to call that crest B. And let's suppose that we have the same amplitude and the same wavelength. I've got these 2 crests that are traveling towards each other. A is traveling toward the right and B is traveling towards the left. That is one snapshot in time, and eventually those two are going to meet in the middle. So let's fast forward a few frames and see what happens when they meet in the middle. A little bit later, crest A has made it to the middle, and it tries to make the spring go up. Crest B has also made it to the middle, and at the same time, it's also trying to make the crest go up. So now what happens? The medium responds by adding the amplitude at those points at the same time. In other words, A and B are going to stretch the spring or the string until I have a crest which is twice as tall, again, if those are equal in amplitude and in wavelength, and we would say that that's equal to A plus B. That occurs only for an instant in time. What happens after those two are passing through? Because B is trying to travel to the left and A is still trying to travel to the right. What do? After they encounter each other, A and B are going to continue to travel in their original directions as if they never saw each other. If there's no damping in the system, then A is going to be unchanged as a result of its encounter with B, and B is going to be unchanged as a result of its encounter with A. They'll continue traveling in their original directions. You could think of this time-lapse view, the first picture being a before picture, the second one being a during picture, during which the two pulses overlap each other, and the last picture being what happens after those two disturbances overlap each other. And if those two pulses are in phase, in other words, both of them are crests, or we could say both of them are troughs, and they don't necessarily have to be equal in amplitude, they just have to have the same relative phase, then we call this kind of interference constructive interference. We call it constructive interference because during the time which the pulses overlap, the resulting amplitude is larger. In other words, I have constructed a wave that has a larger amplitude than either of the original amplitudes.